sketch the proof of this theorem. So X projective manifold. Agent ample divisor.
Could you write it a little bit bigger?
Sure. And we assume that C1x squared agent n minus 2 is bigger than 0, and that on this variety we have a codimension 1 foliation with numerically trivial canonical bundle. Then we have essentially three possibilities, non-disjoint. The first one was that F is uniruled. The second is that F has a first integral, a rational first integral, meaning that its leaves are algebraic, hypersurface. And the third, that F is defined by a closed rational 1 form with coefficients in a flatline bundle and without codimension 1 zeros. So, an example of a variety satisfying this hypothesis is the projective spaces. And the hypothesis Kf numerically 0 is the same thing as saying that the degree of the foliation is n minus 1. So we have this structure theorem for foliations, if you want, on Pn of degree n minus 1, which allow us to give another proof of Servolin's-Neto theorem, classification of foliations on degree 2, avoiding the use of Dulac's theorem. But
in P2 is
degree 1. In P2 is degree 1. And but the method that we use really heavily the condition Kf equals 0. So if we are only interested in foliations on projective spaces, the argument that I sketched yesterday, it's useless if you want to go beyond degree n minus 1. If you want, for instance, to say something about degree 3 foliations on P3, right? So as I explained at the end of yesterday's talk, to try to approach these foliations of higher degree, so for me 2 is already pretty big and 3 is enormous, we are going to do some more projective differential geometry, right? So as I explained, the idea was this simple idea to pick a line on Pn or on P3 if you want, look at the tangency points with the foliation, and try to deform these lines, keeping tangencies with the very same leaves that we started with. So how do we do that? I'm going to explain this construction. I will do step by step. I will start with something that is very classical. I will start on P2 with a very classical construction that can go by the name of, for instance, of Legendre transform. If you pick up old books on differential equations, you're going to find this. And the idea is very simple. So I have a foliation on P2, right? So I take a leaf. What I want to do is to exploit projective duality to define an object on the dual projective plane. So the idea is very simple. I just pick a leaf, and I draw on the dual projective plane the dual curve associated to the leaf. So to each point, I consider the tangent line. It will be a point on P2 dual, and I do this. Of course, well, perhaps that's not a good point to start with, right? This point is there. Of course, we can do that for one germ of leaf, but we would like to understand what is happening globally. And indeed, if you think a little bit, what we are trying to do is to look at the Gauss map of the foliation going to P2 dual, and take this dual, the Legendre transform, would be nothing more than the direct image of our foliation by this map. So if our foliation has degree d, this is a rational map which generically has d fibers, and we see that the direct image is not a foliation, but indeed is a d-web. Meaning that over the generic points, I have d foliations. And there are some special places, the image of the curve of inflection points on the other side, where the foliation has, where this collection ramifies. This collection of distinct foliations ramifies. Okay? So here we have a nice duality that we will start with, I start with a k-web of degree d, I end up with a d-web of degree k. K-web. I can just, well, it seems like a good idea to have a category to work with that is closed under the finite map. So it just, well, foliations, webs, it's the same thing. It's just.
But you could also take a covering of P2 dual and link the web to a foliation not on P2.
Sure. This construction is essentially this following. No? That's a good point that I was going to make. You have here the incidence variety. And when I start with a foliation or web, I can look for the graph of it and restrict to it the contact structure on the incidence variety, which is nothing more than. And now on the graph of the web or of the foliation, it will be a surface on this free manifold. You just restrict the contact form that we have here, and you get a foliation. But then these maps are not one-to-one. When I try to project them, it can happen, and it will happen, that you have something that's kind of multi-valued foliation. Okay? Nice. But we're not, it's not the subject of the course foliations on dimension 2, as the integrability is empty, and we are trying to discuss implications of the integrability condition. And if we try to go to Pn, we can, of course, just repeat the same construction. Just take the direct image under the Gauss map of our foliation. But now, there is one subtle point. While here it was quite easy to understand this map, it was a D21 map. Now, even the degree of this map is a non-trivial thing. It's no longer the degree of the foliation. We saw foliations of degree n, the linear pullbacks, such that this map is degenerated. It's not dominant. And indeed, the degree here of this map is a quite nice invariant that we should look at it, we should explore, but I will not do it in this first half. But this is one possible generalization. But let's look here. This case of P2, there is something happened, because here we have an identification between the incidence variety with this guy and with the projectivization of the tangent. So we could also try to mimic this construction. Well, I start with a foliation, look at the graph, and take the direct image. We could try to do this construction with this setup. So let me try to be a little bit more precise. Instead of putting the dual projectives plane, it's natural to put also the Grassmannian of lines on Pn. Go to the incidence variety, which is now nothing more than the projectivization of the tangent space of Pn, of the tangent bundle of Pn, since a line is determined by a point and a direction. And if I start with a codimension 1 foliation, let's just put dimensions here. This thing has dimension 2n minus 1, and this thing has dimension 2n minus 2. So let's just recall that a foliation is a one form, something that eats vector fields in the breakfast. So a one form defines a function here. So it defines a divisor here, which we can try to take the direct image. And on this divisor, we also have a contact structure here, something like a contact structure. So if I take with a foliation here, I can lift it to a divisor here. The fiber over a point will be just the tangent, the projectivization of the tangent space of a leaf. So the fiber over a point will be a Pn minus 1, minus 2, Pn minus 2. And we can just try to take the direct image. So what I'm doing, I'm taking a leaf, and to each leaf of the foliation, I'm associating a divisor on the Grassmannian, such that, which is the union of all the tangent lines to this hypersurface, right? So I start here with something dimension n minus 1. I end up with something of dimension 2n minus 3, which is somehow fibered by Pn minus 2. Okay? And this construction can be seen as a generalization of that, and has the advantage that I take a degree D foliation and obtain a D web here. Okay? But it seems so far not very clear the relation with this construction. But what is a web? Remember that here we are in, if you want, let's say n is equal to 3. We are on a 4-dimensional space. So what's a web? I have a bunch, a codimension 1 web. I have a bunch of hypersurface. I have a hypersurface. And then through a given point, I have the hypersurface. So here I have some intersection. And I will have some more intersecting. And we can, instead of looking to the web, to the D-web, we can instead look to the axis of this web, meaning the intersection of leaves, right? So this will define another foliation on this space, the axis of this web. Will be a foliation of codimension smaller than or equal to D. Right? I'm intersecting the hypersurface at a point. And what this foliation measures is exactly that. You see? Because one leaf is just the collection of all lines through a point and through a variety. All lines tangent to a variety. And these are the leaves through a point. And we are intersecting them. Right? So this is the foliation that I want to look at. And the thing is that, you see, if the degree, let's suppose that n equals 3, we can ensure that this is not the foliation by points, just by like that, if and only if the degree is at most 3. So we have some space to go beyond degree 2 on P3, and we can go until degree 2n minus 3 on Pn. Okay. But again, we have to ask some questions. Of course, when this axis has the expected codimension. Can we classify the exceptions? Of course, if you want to use this kind of construction to classify foliations on Pn, this is the first question that you have to ask. And note, for instance, if I am P3 and I have a foliation that is F is a linear pullback, then let's give a name to this guy. F tang tilde, the tangential foliation to F. I will put a tilde there because this is not my final construction. Then it's a simple exercise to see that the codimension of F tang is 2. Why? So it's a linear pullback. So here I have a P2. I have a foliation on P2, and I have this projection. So suppose that you take a line. I can suppose that the line is on this P2. Otherwise, I take a P2 containing that line. It will have one tangent with the foliation on P2. And will be, of course, tangent to the foliation here. But now I can just move this line on this plane as I want. It will still keep the tangency with the same guys. So I have here a lot of tangencies. But if I move this line, because here the tangencies will be something like this, and then I can just move the line, no matter how high is the degree, in such a way that it keeps on the same line. And indeed, this is the situation. If we are on P3 and the codimension of F tang is 2, in degree at least 3, we have a characterization of linear pullback. This was somehow, it's not very hard to show. But then there was a case that puzzled us. Suppose that I have something of degree very high, degree greater than 4, let's say. 3 enormous, 4, it's beyond reach, right? And we would expect that the codimension is 4 on a 4-dimensional space, foliation by points. But what can we say if it's the foliation by lines? It's a foliation by curves. Because if it's a foliation of codimension 2, dimension 2, we know what it is. But in this case, we are really puzzled. We start making computations, deducing very funny things, like, for instance, you take a degree 4 foliation, you take a line, so you have 4 points, right, of tangency. And we also have 4 hyperplanes, the hyperplane of tangency, and we verified by computation that the cross ratios are the same, showing that we were in the wrong direction, right? Things were getting complicated very fast. But the point is that this construction, and also this construction is bad, because we had this problem of classifying foliations with kf equals 0 or kf small, let's say equal 1. And we can't see how to generalize these to an arbitrary variety. It seems very hard. And even if I only want to understand foliations on Pn, I could, instead of working with lines, I could work with another curves. The point is that introducing some redundancy, the things get much more clear. We should not look at lines, because they somehow obscure things. We should look instead of lines with coordinates. We should keep the coordinates. Since we want to compute, it's already a good idea to keep coordinates. But it turned out to be the good viewpoint for what we want to do. So instead of doing this construction, which is very particular to projective spaces, to lines, let's instead just look at morphisms from P1 to X. I'm already going to an arbitrary variety. Seems that we're not gaining nothing, even if I will show you that even in the case of line, keeping the structure of the map will make things clear. And the point is that there is a rich theory, in very round, very, very nice, which explains how is the space of these guys, as soon as you impose some restrictions on the pullback of the tangent bundle by F. So if this guy, which is a line bundle on P1, this guy is a line bundle on P1, I can always write something like this by Grothendieck-Birkhoff or Birkhoff-Grothendieck theorem. Now, if all the AIs are positive, then we have this, we have then we have quasi-projective variety more P1 is smooth at F and of dimension such that which parametrizes morphisms from P1 to X. This is very basic deformation theory. It's kind of the dream case of deformation theory. Better than this, only deformation of points. And then, the thing is that in this case, as this equality suggests, there is an well, this, in which sense this parameterized morphisms? In the sense, in the following sense that, let's call here M, containing here. In the sense, in the following sense, I have this M, and I have here M times P1. I have to think the point of here. The points of here are morphisms.
M is
well, this indeed is this. We can just define this guy. It's a scheme, blah 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 blah. I'm saying that there is an irreducible component which parameterizes the deformations of F. And this thing comes with an evaluation morphism, right? I just taking a morphism G and a point X on P1. Am I looking to X evaluated at G evaluated at X? So we have this thing that parameterizes morphism from P1 to X in the sense that it comes with this evaluation morphisms. And everything is algebraic, right? And the point is that this tangential foliation that we defined on the Grassmannians of lines, we should look at it on this space, on M, this space of morphisms. When we restrict two injections of lines to Pn, what will be the difference between the two? It will be only the following thing. This thing will be the quotient of that one by the action of automorphisms of P1. And in some cases, we should avoid our reflex to take quotients, as quotients tends to make things harder. That's one idea that I learned from this. Do not take quotients, never. It's not good. Okay. So, but then how do we define that foliation? The thing is that the thing gets much more clear, because here, on this space, I can try to understand what is the tangent space of F at M. And this is nothing more than the F star of Tx. Oh, H0, sorry. It's canonically isomorphic to H1 P1 F star of Tx. And it's not very hard to see that, at least to get the heuristic. You look at a map. Now you're deforming your map. So you can take a fixed point on P1 and see how this deforms. So you take the derivative to define a tangent vector on a point of X, on a point of the image. So that's it. And now the nice thing is that this guy, since I have a foliation on X, this guy comes with a natural sub-vector space. So without doing much, we have just defined a distribution on this guy. A distribution on M. To each vector, to each tangent space, I just defined a sub-vector space. And these are exactly the deformations such that the point will continue along the leaf that it starts with. At least if you are away from the singular set, as we can always do because we are going at the end to work at the generic point. If we have this assumption, this thing is big, has dimension at least n, and that's good. But that's exactly the point. And indeed, it's the same thing that we were doing before, right? It's not immediate to see it the first time, but the point is that if in the previous construction I deform, imagine a small deformation, keeping the same tangencies, and then you have here the parameter space of the deformation, D, and then you just pull back the other foliation, the foliation that you had. You are going to see that as I'm fixing the tangencies, it will appear some numbers of, when I pull back the one form, the tangencies will give rise to zeros of the pullback form. And then when you divide by these zeros, you make a simple computation, and you see that the foliation that you get is everywhere transverse. And we are really in this situation. But then here, I want to insist on that. It's better. Because here the foliation is almost horizontal. Now in this situation, when I take a deformation which respects this distribution, a deformation of f contained in this distribution, tangent to the distribution, when I pull back the foliation, I get the trivial foliation, the horizontal foliation. It's not almost horizontal, it's horizontal. Okay. There is another way of viewing this construction. So here let's look at M. I have here X, and I have here this P1 bundle, this trivial P1 bundle over M. And now here I have the evaluation morphism. I can take my foliation here and pull back it under the evaluation morphism. Right? The codimension preserved by, well, I didn't say, but when this guy, when they are all non-negative, this evaluation morphism will be dominant. And so the pullback of this will be still a codimension 1 foliation. It's this. What is this M? It's just a space of morphisms, right? And here is just the morphisms together with a coordinate. What I can do with it? Just evaluate. So a point here will be Gx, and this evaluation at Gx will be Gx. Okay? So we pull back our foliation, I have a codimension 1 foliation here. And we can try to see, we can just try to take the direct image of this foliation. Again, we are going to have a web, we can look at the axis, and we have the same thing. So this is the foliation that we are going to call f-tag. No children right now. This is the object that we want to look at. And the nice thing is that it will be, I said here that it was a distribution, but it's indeed integrable. It's easy to see. You have just to do nothing. And the nice thing is that we already have this dimension for free. The thing that was kind of making us crazy there, taking cross-ratio here, there, comparing, it comes from the definition now. It's the same. Well, there is this automorphism.
Yeah, but you have.
We don't have.
If you there, you could take the quotient.
I would take the quotient if I want. Yeah, I'm trying to forget this one. As nice as it is, but. Of course, all this has to be. We have always to choose F very generic. You should not take a special F because things can get complicated. But we can just look for the generic F and everything will be uniform. Right? So we have to study this foliation. And it was somehow a surprise to us that some old work of ours with Servo and Isneto about what we call Gobillon-Veil sequence of foliation was quite related to this. And the techniques that we used there could be applied here to say something about this foliation. So the first question that you do, well, okay, you have a foliation. Can you say something about, we know the dimension. Can we say something about the closure of leaves? In general, for an arbitrary foliation, we all know that it's very hard, right? But here, somehow, this extra structure gives us an answer. So we have this result, for instance. So let L be a generic leaf of F-tang. What are the assumptions? The assumptions are that, right? I start with a morphism which has all guys non-negative. Then, the dimension of the Zariski closure of this guy inside M is the dimension of L plus epsilon, where epsilon belongs to 0, 1, 2, or 3. It's kind of, to say at least, we don't understand the thing, but since we don't understand very well what we are doing, it's kind of surprising us. And the things are very interesting because we can also do this. We can always look F-tang restricted to the Zariski closure of F, of L. And these cases, each one of these cases, this case, of course, is the case where all leaves are algebraic. So this is somehow the trivial case. And these cases are, this foliation will be always transversally Lie. And these cases, well, I'm meaning the restriction of F-tang to L bar will be transversally Lie in the monomorphic sense. And these cases are, of course, the abelian, affine, and projective Lie algebras. And indeed, the proof, it's not very hard. I want to insist on that point. It's really, you follow your nose. As soon as you understand that, that's the good question to ask, right? But when you ask that, you follow your nose and you prove that.
How do you stop?
Hmm?
How do you stop?
The point is that although this thing seems to be very abstract, at the end we can just write down this equation. And this says, what's the equation of this foliation here, F star F? It's just a one form that to take this expression. So let's say I have a coordinate z here, and the one form will be something like dz plus some omega I zi. From I, omega I will be rational on the base, right? With poles, perhaps. And this I will be finite. The poles, well, and here I have also a P, Pxz. And as I said, these are one forms on the base. So this will be a polynomial in Z and rational in X. So these are one forms on the base. We can look at this collection of one forms and see what foliation they define. This collection of one forms define the foliation F-tang. So you restrict to the Zariski closure of that, and we start to prove things. Remember that this F-tang also is defined by the following property. When I restrict this one form to the leaf of F-tang, this form will become just dz, proportional to dz. That was the definition of F-tang. And then you can start to compare the algebraic relations that these guys have on the whole space with what they have on the restriction to L bar. But essentially, by definition, as we are taking the Zariski closure, things that we use to vary will become first integrals, and then will have to be constant on the L bar, and then you start to say that, well, in the restriction to the L bar, this guy does not depend on X, and this forms every algebraic relation will be indeed a constant relation with constant coefficients, and you'll go like that. And you will find the structure equations of the transversal algebras, right? So it's really, And the even nicer thing is that when epsilon is positive, this information says that our original foliation, since you see that already here when I wrote that, there is a very intricate relation between this foliation and the original foliation. And this translates to information on the original foliation. So when f equal 0 means that our original foliation, f, has a subfoliation by algebraic leaves, which allow us to reduce dimension. When epsilon equal 1 and 2, f is transversally affine. And f, always in the meromorphic sense, f is transversally projective. Okay? So, from this, we have just proved, well, once we prove this and also these implications, we are by no means completely evident, but have to do some work. We prove, for instance, that a foliation of degree 3 on P3 is either come from dimension 2, because it has a subfoliation by curves and will allow us to go to dimension 2, or it's transversally projective. But then, when we do have this transversally, so we still want to do a little bit better. When we are in one of these cases, all these cases are indeed transversally projective. Transversally affine is transversally projective. So we have a transversal structure on the foliation. And then when I take a generic line, we have a transversal structure on the line. So this leads us already. Here we have this foliation F tang. And we can try to define another foliation by what? As soon as I know that it's transversally projective, I can look at the restriction of the transversal structure to a line. I have a projective structure of it, and I can go to the moduli space of transversal structures.
On the line.
On the line. If we had to do that, that's another point where we got advantage by having this extra structure, this redundancy, instead of looking at curves, looking at morphisms, because we don't have to do that, thanks God, because this would be a mess. It's hard to understand this guy. I'm talking here about rational projective structures. So we would have to do GIT and no. We have a coordinate. So it's indeed, it's just, if you want, a quadratic differential. Because you not only have a line, but have a coordinate on the line. And this defines first integrals for my foliation F tang. This map is algebraic.
But this is a map to where, because it's a quadratic differential, so
Of the degree is born. The degree of the polar set is born. It's essentially the degree of the singular set of the project structure that I started with. The projective structure is fixed. So you are in good shape. You have really an algebraic map with algebraic fibers. And then let's just do a zoom. Here I have L. I have L bar. And I have perhaps the leaves of this guy that must be at least as big as L bar. The leaf of this foliation passing through that point. And again, we lower our heads and compute. And the fact that I have here somehow a trivial deformation, which is really the horizontal foliation, and I can deform this, do a small deformation, where the projective structure does not change by computations, simple computations, we produce a vector field over the Riccati equation defined by the transversally projective structure on this line. In other words, doing this computation, we can show that we have this line. Now, I'm seeing it on X. We have a neighborhood of it where our foliation is defined by a closed meromorphic one form. Essentially by this comparing the variation of the projective structure. Don't ask me to explain why this happens. I don't know. I can prove it, but I can't explain. But OK. So in the case of PN, this is good enough to show that our foliation is indeed defined by a closed rational one form. Again, this guy, this neighborhood, can be taken pseudo-concave, and we can extend to the whole space to obtain that the things are transversely Euclidean, not just projective, to show that our original foliation is defined by a closed rational one form. There is one, so this is already is going on the right direction, right? We are showing that, for instance, let's just translate. If the degree of f equals 3 on P3, then we have just shown that it's even given by a closed rational one form. It's the case where this foliation f tang epsilon is positive, strictly positive, or comes from dimension 2, which is the case where epsilon is 0. Of course, this works not only on degree 3, it works on degree smaller than 3, but that's why we already knew. Indeed, on this case, we would like to say something more. Because remember that on the case kf equals 0, we were able to show that the subfoliation that we produced there without much control were indeed by rationally connected E's. Remember, we were using to do that Bogomolov's, Miyaoka-Bogomolov-McQuillan. So we can do that also here. And we have just to adapt Morenbrake argument. What is that? So we have, I want to discuss now a little bit this case, right? So what is happening? So let's, perhaps it's easier to well, let's, so again, I have this foliation here on M, which is now by algebraic leaves, right? We can define this foliation, we can lift this foliation by algebraic leaves to a foliation by algebraic leaves tangent to the foliation pullback of F. So I have here now a subfoliation, G, contained here, which is by algebraic leaves. And now we want to look at the image of these algebraic leaves back to X. Two things can happen. Remember that the pre-image of a point here can be pretty big. It will be pretty big. In the case of of lines. It will at least contain lines through that point, morphisms of lines through that point. So it's pretty big. So let's look what is happening at a leaf here on X. I can have either, I have at least one algebraic subleaf, but I can have many. Right? If I have many, then it's not hard to see that what I want to show. Well, it's not hard to see that this leaf is algebraic. Well, that they will generate an algebraic subvariety contained in the leaf. If instead I have only one, something very strong is happening, because then this will define again a foliation, but which we can deform, essentially by definition. This foliation still allows, I can still deform lines along the leaves of this foliation. This essentially will say that and we'll be giving information about this foliation G, right? Oh, sorry, I realized that I'm doing another argument. I'm showing another thing, sorry, but okay. And how this indeed, I'm trying to answer the question that I started with. What can I say when this foliation F tilde tang has dimension 1 and the degree is high? This says this, that this foliation is positive, and they say that G, degree of G, so here let's say on P3, that degree of G is equal to 1. So means that F is invariant by an action of C. But sorry for that. The point that I was trying to make is was not this. I was trying to show you how to produce rational curves contained in leaves. Sorry about that. So the situation is as follows. So imagine that you have a rational curve, f of P1, which is away from the singular set. Then we can do this construction of the end of the second lecture, this Bogomolov's-McQuillan graph construction. So I can construct a transcendental variety, which is just the union of pieces of leaves along the f of P1. So this will be a transcendental variety. And now the nice thing is that the deformations, the leaves of F tang, the deformations of F which follow the foliation, is the same thing as deformation of this curve, just now forget the morphisms, on this transcendental variety. There are two equivalent viewpoints. And when I have sections for this guy, I'm not just saying that I have sections for this, but I have sections vanishing at a fixed point. We can deform this curve, which is algebraic, here, keeping the point fixed. And then we can show that indeed this thing will generate an algebraic variety. In the closure there will be an algebraic variety containing rational curves. And then is where enters Mod is bend and break argument, which is very nice, and which is essentially the following. Imagine that you, in this situation, you can produce a C times P1. C will be, or T perhaps, the parameter space, times P1, which will come with an evaluation morphism to X. So you can think this as a curve. The evaluation morphism, it will not be necessarily holomorphic. It will be rational, because we did some kind of algebraic construction that took something and took the Zariski closure. And when I pull back, so here I have this, when I pull back my foliation, by construction, I have something like this. I have the fibration, and since I'm deforming the morphism along the leaves, it will be just the horizontal foliation, right? When I pull back the foliation here. But this morphism, since I'm deforming a line fixing a point, it has to contract one of these curves. It has to go to a point, because by construction of the morphism. But we cannot map something of self-intersection 0 to a point by a holomorphic map. This means that there are some indeterminacy points. When we blow up these to resolve, we see that this line, the image of this line will be a curve, and it will have to be invariant by the foliation, because here the foliation is just the horizontal foliation. When you blow up, there is no singularities, there is no critical points. Everything that appears as an exceptional divisor is invariant. And so the image is also invariant. And this way, in this setup, allows you to produce rational curves. And indeed, this gives essentially a proof of this theorem, Kf equals 0. Same conclusions as the end of the last talk, uniruled, algebraic, or closed rational forms, under the assumption that X is rationally connected. So this circle of ideas not only allow us to prove this theorem in another class of varieties, but also show us how to deal with foliations on Pn of codimension 1 and degree at most 2n minus 3. So we can deal with foliation of degree 3 on P3, and we can go beyond in higher dimensions. So I think I will stop here.